So welcome back everyone to the second part of the lecture, which is about nowcasting. So what is nowcasting? Well, as you saw in the animation, where we showed how much information is available at a given outbreak compared to what is registered somewhere or information which is already available. This is a more humble attempt to try to figure out what's going on at the moment, instead of saying that you want to really be able to predict what's happening into the future. And so we say it would be an ideal setup if there's no reporting delay, no delays in that sense. So this is stuff which is just sort of the word nowcasting. It's just a more modern word for reporting delay adjustments, which is something which is done in infectious disease epidemiology for quite some time. It was had a revival during the AIDS HIV epidemic in the that's where most of the work is done, is in the early 90s, late 80s. And it's the term nowcasting is based on a paper from 2011, where it was used for the H1N1 influenza outbreak in 2009. And what is maybe interesting for some of you, I saw some of you in the survey filled out that you are following the actuarial line, is that there is a close connection between nowcasting methods and claims reserve modeling in actuarial science. So reporting triangle, runoff triangle, chain ladder, that's terminology which some of you might recognize while I go through this. So introducing some notation, let's say that NTD here is the number of observations which occurs on day T, but only becomes available in the central registry, or the registry we are using for our analysis, with a delay of capital D days. We will assume that capital D is a discrete, so it's 0, 1, 2, 3, 4, and for convenience we will say there's a maximum delay, and we will call that capital D. And T, the time, the calendar time, is running from T0 until capital T, where capital T is the most current time point. So that's what we call now. So today it would be the 20th of June, it would be now. So that would be capital T, and T minus 1 would be the 27th of June, and so on and so on. So one problem is that if we have the NTDs available is, well, if the delay is greater than T minus capital T minus small t, then actually this observation will be unknown to us at the moment, because it's simply not reported yet in our database. You'll be able to see that here. This is the so-called reporting triangle. We have on the x-axis the delay. It will be 0, 1, up to capital D, and then we will ignore whatever is coming. There are no longer delays possible than this. And then we have calendar time up here. So capital T, that's the x-axis component here. Sorry, the first component, that's the most actual time point. And those who have a delay of 0 days, they will be available to us today. But those who have a delay of 1 day, we will not see, because we will only see them tomorrow. Same for if you have capital T minus 1, we will see those with a delay of 0 days, those with a delay of 1 day, but those with a delay of 2 days we won't see. Right? So you will see that this is the report. That's why it's called a reporting triangle. You will see that this is the front here. These will be observed, but this part here is what we will not observe. And we shall call the sum of what we do have within the reporting triangle here, that is the information about the total number of cases in a particular row, n small t, given the knowledge at time capital T, that what will be available to us. So that's the sum here. And what we really want to is to take that capital T here until the total end, so until infinity, but actually we know that it's observing it to capital D out, extra time points out there will be sufficient. So, but we'll for convenience say it's NT infinity will be the true number of cases that we will observe at time that happen at time t, but we will ultimately see, right? So what is missing will be nt infinity minus ntt. That's what will be the part which will be missing, which will be the shaded part of the reporting triangle, right? So going back to our original slide here, is that ntd is unknown when d is bigger than t minus t, right? And we will introduce the notation to say that n, the sum overall which are available at a particular time point, capital T, so our now, that's we will call ntt. And so what we really try to do, and that's the aim of the nowcast, is to do a prediction of nt infinity based on the number of cases which are actually available. And nt infinity will be so one sum over one row in this reporting triangle, so from d naught until d infinity, but as we said, we for convenience cut it off at capital D days. We will have to do this sum, and some of them, but not a lot of them, will be available to us, and some of us will not be observed, so those we don't know, but that's what we really want to sum up, right? So if we are at a particular time point from here and going down in the reporting triangle, we will actually have observed all delays. So there's no there if there's capital D is the maximum possible delay. So there we actually seen this nt infinity. We actually have observed it for here. So there's no need to do nowcasting for this part of the triangle, but it's of course necessary for this part of the triangle. And typically that's the ones you would be most interested in, is of course those which are closest to now. And that's where the most part is missing, right? So what are the methods that you can use for the nowcasting? Well, the first thing is you need to know sort of like what's governing the delay, that what will be, that it will be 0 days, 1 day, or capital D days. What is governing that? And that's very similar to the incubation time period distribution, which we looked at in the part A of this lecture. We will say there's the reporting delay of an event follows a distribution, and it's a discrete distribution with a given probability mass function. I will say we'll call that FD, and it's simply equal to PD some probability, so it's between 0 and 1. And we will start at 0, so it's possible to transmit with 0 delay, and it will be a maximum possible delay, and delays which are larger than that will not occur. What is an important assumption, we will assume that there's a time homogeneity of the delay distribution, so it won't change over the course of, for example, the epidemic. And we will denote with capital F the cumulative distribution function of this probability mass function, right? So if this is the probability for 3 we want, for example, then we will sum up the probability that it will be, we will sum up the probability that it's 3 or below. That's what we will get here. And we will do that by summing up the probability for 0, 1, 2, 3. So that's what this formula here says. And then there's a very simple and a very intuitive way of actually trying to find an estimate for how the total number of cases is. Well, you say that's what we observed. So we observed, maybe say, let's say 5 cases by now about time point small t. And we know that the time point we're trying to predict, let's say that's yesterday. So usually we say with a delay of 1 day, we have maybe 50%, or no, maybe take a smaller number. We after 1 day delay, we have typically 10% of our observations available. So we would take our 5 cases and divide that by 0.1 to say how much is the total number, which we would expect. So this is a very simple proportion division. So a very simple estimate. So number of caveats here. First, I use here the f hat. Please note that I always use a hat in order to say something which is estimated for data. And this is also because this is an estimator, so I put a hat on it. And if there's another hat, it's either because the quantity is observed, like this one here, or because it's a random quantity, and we write it up in a probabilistic model type of way. So standard notation for statistics for this. But one thing is important, is that you want to estimate this cumulative distribution function. You need to take into account that if you want, for example, the delay of 2 days, then if you simply sum up everything with a delay of 2 days, then those observation here, that would be 0, 1, 2, it would be out here. This one would be missing. Sorry, 0, 1, yes. These two would be missing, right? So only those with a shorter delay would be delay would be available. So if you don't take this into consideration, you will get a bias, and that observations are missing towards the end. This is something which is called right truncation of the observations. So this is related to survival analysis as well. Those who are longer, where the small t plus the d is bigger than capital T, those will not be available. You will see them later, but they're not available at time capital T. So that's what is called a right truncation. Right. So that will, what we had here is one very simple estimator. There's another one which is more a bit probability model based, is that you will say that the number of observed cases, which we will see, is a binomial distributed random variable, with this being the size parameter and this being the probability parameter. Please note that we insert here the estimate because we're already aiming for an estimate for all of this. And what we really want to do now is we say we have an observation on this. This one here we assume is fixed. And what we really want is to estimate the n in the binomial distribution. And one very simple estimator for this is, of course, this one here, but you can do it a bit more sort of likelihood-based inference, as well as simply to say, well, what you're going to do is you're going to try out every value of the binomial distribution where you start with NTT, because that's the smallest possible, and you're going to start increase n by one by one by one, and you always look at what's the binomial distribution for this, and you take the one which gives the best, the highest value, because that's what you think will be explaining the observed value as well. I'm sorry, here the hat needs to go. That's because that's no, sorry, the infinity needs to go here. That's that's a mistake. I should have written infinity here. Right. So that's one way to do the estimate. And then there's maybe also a statistical one, which some of you will find quite confusing because you never heard about such type of models. But for some of you which had, for example, categorical data at the statistics lecture, there you will recognize something like this. But let me still try for also some of you who may be interested in statistical methods but haven't met something like this. I will try to explain a bit, but I have to say this is a bit beyond what we expect you to know by mathematical theory, at least, but I think it's still good to know the applicational framework for this. So what we have here is we will say that the number of observations who have occurrence of the event of interest at time t and a delay of d days, where t runs from 0 to t, capital T, and the delay is between 0 and maximum of d. But then again, please remember, because the reporting triangle is missing here, those observations cannot occur. So I'm not going to write this in array form, because here the d, because of the reporting triangle missing that part, it's cut off like this. Lambda of t will be the expected number of new events occurring at time t, which will be of interest, and fd will be our reporting delay distribution as we defined it like here. So maybe I should write fd here instead to make it clearer. So this one here should be a small f. Okay. Right. So we will say that the number of the number of cases, it will be a Poisson distributed random variable. So that's a count data distribution, and it has one parameter, and the parameter of this is the mean of the distribution. So what we're really doing is we're parameterizing the number of observations. We will say it has a certain mean, and this mean is given as a product of two things, namely, first of all, the lambda of t, which is the expected number of new events, and then how big a proportion we expect to see on a given delay, small d, right? So that's the first part of the model we have here. And altogether, there are t plus d plus 2 parameters to be estimated. And once you see something like this as a statistician, you say, okay, this is good. We need to parameterize the mean because it's a count data distribution. The mean has to be smaller than 0. So the mean doesn't have to be an integer number. Please don't make the mistake of thinking that, because it has to be an integer. So the parameter of the Poisson just needs to be bigger than 0. And then you can use a so-called log linear model or a generalized linear model to sort of, instead of modeling this, you model the log of this, because then you're ensure that if you take the log of this, you will have log of lambda t plus log fd, and you can simply parameterize this to say this is a function, something which is a function of time, and something which is a function of delay, right? So you can do a model like this. Maybe just a few more details about that. I think we have the time for this. So I will new share. I will share the whiteboard. Okay, where is the whiteboard? Here's the whiteboard. Nope. Okay, trying that again. Bit of problem share screen. Whiteboard. Here we have the whiteboard. Okay. So just to check out where we are, like this. Right. So remember we said NTD. It's going to be a Poisson distributed random variable with lambda t and fd. For some reason have the okay. I have to move the bar here. So sorry about that. I'm still trying to learn how to use the Zoom whiteboard together with the Wacom board for drawing. So like this. So we had the product here, and since this is the parameter in here, that's what is the mean, right? So we know that the expectation of NTD, that's going to be equal to lambda t times fd, right? And now we decided to parameterize this by simply saying we take the exp, so that's the natural exponent of log, and please note this is the log e-based logarithm, so it's a natural logarithm, but statisticians always write this one as, instead of writing ln, we always write log, because for statisticians there is no other log. But I can fully understand if that's confusing for some of you which haven't used the log that many times. So again, I have to remove this and remove that. And then it's plus log of fd, right? Like this, right? So you could also say this is the product of x log lambda t times x log fd, right? And of course, x and log, they cancel, they are the inverse of each other, so that would cancel out. But the nice thing is that with this parameterization, we ensure, so what we will do is we will define something like this. That will be, let's say, I don't know, alpha t, and we will define this here as beta d, right? So we will ensure that, because we always then take the x of what we will get, we will ensure that both the lambda t will be bigger than 0, and we will have that fd is smaller than bigger than 0. So I mean, one small technicality is, of course, that it's actually possible to it's not a unique parameterization, of course. Note that if I had taken like k times lambda of t and then have simply said it's 1 over k times fd, then the result would still be lambda t fd. So that means it's not possible to directly really say what is fd here, right? Or what is lambda t here, but what you can do is to fix that this becomes clearer, and I'm just going to say this means that lambda t and ft are not uniquely defined. Okay, but what we could do is, we can demand, let's say, that we'll say fd star is equal to fd divided by the sum from d small d 0 to capital D of all the fds, to ensure this has one advantage is, first of all, we fixed the parameterization in some sense, so this here is not possible anymore. And what we'd also ensure by this is to say that, well, it will now be, it's not all, sorry about this one here, we would still have that it's positive, but what we would have is that it's more bigger than 0, and fd star is not only bigger than 0, but it will also be smaller or equal to 1, which is our demand, because it's supposed to be a probability mass function, right? So with this, we looked a bit more in detail at the model. This is a so-called way of specifying this. So you can, of course, say your parameter vector is consisting of all. I'm just going to delete this here now and continue drawing. Namely, is that we'll say, okay, the parameters we now have, well, let's call that, we will make a vector theta, and that's equal to, starts with lambda naught, goes to lambda capital T, and then we have f naught, f capital D. That's what is in our vector, right? So that's our vector of T, capital T plus capital D plus 2 parameters. And then we set up a so-called likelihood function. That's one way to say how we will estimate this model. And we will say, well, given our model, the observations are going to be independent. And what we can write up is a function in all of the parameters, is that we say, because of independence, we say the probability mass function of all the observations we see is, and now I'm going back to lecture number 2, is simply the product overall probability mass functions for all the observation we will see. So that will be 1 to capital T, and it will then be the product from D from 0 to minimum T minus small t and capital D, right? Because we cannot go beyond D, because that's when the last delay was possible. And we will say this will be the probability mass function of the Poisson distribution evaluated for the data that we will see NTD, and the parameter will be a function of everything which will be in this theta vector, right? So we have to set this up for each For each observations, we take the values from the theta vector, and we will, given the expectation as I showed you on the previous handwritten stuff, you will want to then maximize L of theta, right? So you need to sort of do something, try to find this theta parameter. So it's an optimization, multivariate optimization problem with t plus d plus 2 components, unless you use a more sparse parameterization. So you have to have enough data for this. But this is one way to try to maximize this way the probability mass function of the Poisson you can find, for example, on Wikipedia, right? Good. So that's something you can implement, or you can alternatively also use R directly for that, since this is a GLM. So I'm going to clear this, and I'm going to go back to the slides. All right. So here's an example of how to do this for a data set. So the data set is some HIV registry data from the Center of Disease Control in the US, from which was analyzed in a paper by 1989. It contains an analysis of about 6,000 MSM, so men who have sex with men, and they are classified by quarter of diagnosis. So each year is divided by into 4 blocks. So January, February, March is the first quarter, and so on. And then here we have the number of quarters between the diagnosis and the report to the CDC, right? So you can see that things worked a bit slower back in the end 80s about how fast transmission was. So that would be, for example, the third quarter of 1987. These were the number of cases which were immediately transmitted. This is the number of cases transmitted within one. Within this would be the same quarter. This would be within the next quarter. The others are missing because now you are beyond now. So here actually you would usually have one more cell here, but since this is not complete, and I think we're just beyond this one, for some reason that one is missing. The sort of 487 is missing here in that paper in the data set. Right, so you see this typical reporting triangle structure here, that NAs means not available, or is that it's missing. And you see sort of like most of the cases are delivered within the same quarter, so that's good, but some of them are a bit later, right? So you can, if you want to look into the code of the lecture, which I will not, I think for me it was easier to simply just put them on GitHub and not try to upload it each time here. So I will put up the link to the GitHub, and there you can find the R code to do this if you want to use this function. If you don't want to do the optimization manually for the theta vector and just use a function GLM, you can look into that if you want to see how this is done. But it's not so important, at least for the moment, because it's a bit more difficult to use the GLM function. What is important is that there's also an exercise where you should try to do something like this very manually by simply calculating one of the values here, but not using a GLM, but in a different way. And what I show here is that you go back to a particular time point there, like here, you see that the effect of the delay adjustment, which is the pink line, they are really on top of the blue line, which is the observed number of counts. But from here on, you start to have bigger discrepancies. And here you see something like this also, that you go down. And this is also what we observe typically for the epidemic. You see that this is looking as if there were no cases, but actually, this is just reporting delay. And if you use some scaling procedure, this is what you really expect there to be, under the assumption that the delays stay the same as they were before, the time homogeneous delay assumption. I also show some prediction intervals, but these are not important for this class here. It's just good to know that you also should always try to say something when you do a prediction, that you should also have some prediction intervals. But this is beyond the scope of this course now. Well, just a bit of discussion here. In practice, the delay distribution often are time inhomogeneous, so they're not really time stable because there are things happening. Overload of the testing system could be one reason, or that there is some intervention in order to ensure that reporting is faster, and so on and so on. So sometimes you also need to think about how you can actually parameterize time changes in the reporting delay distribution. And then, of course, please also remember that some of the reports at the end, if you had to do the back projection, we said some of the reports will not be available. So one nice thing is that you can combine these two stages, that you in step one do a sort of a nowcast procedure in order to sort of scale up the function as it's supposed to be, and then in step two use the back projection, which we discussed in part A, to do the projection back on the time of exposure, which was the interesting part for you. But again, please also know that this convolution, back inverse convolution, where you say you have one event and then there's a delay, and that's the stuff you observe, and you have some idea about the distribution, that applies to many other settings, not just exposure and incubation period. And then you see symptom onset. There could also be other things where you want to do back projection. Right, here's a small exercise, and maybe just to sort of finish all of this is I just want to show something then which we did for the AHEC outbreak. So that will be here. I'll just simply scale it up. So here's the example of the red one is the true number of hospitalizations, which we know afterwards. The blue one is the ones which we have observed, which we observe at the moment. I will start here on June the 1st. That's where we will start our the nowcasting. And then there's always this yellow line where you do something about, this is such a nowcast procedure where you try to predict what it will be, what is the truth based on the incomplete data that you have available, together with some uncertainty intervals. And then you can see how for each day, sort of this is the days moves on. We usually don't show for the 0 delay, 1 delay, 2 delays, because there's simply too much uncertainty, so that can be interpreted in a nice way. But you see that you get such estimates here with such simple methods. We used a bit more complicated things here because of changes in the delay distribution, but just to sort of show this is the stuff you can do. And then here's you, for example, also see that people start to get worried here again because it increased, like here. But this was, for example, as an example, just some federal states which had not reported any new cases, and there it increases because they had much shorter delay, because they were still very working. They didn't have a big backlog of cases they needed to work on, so they were very fast at transmitting, also because of computer software and so on. So this is the stuff you, of course, need to know, that there is some heterogeneity in the reporting, but we assume time homogeneous reporting, of course, as I said, because but for many practical cases, you need to know what is the consequence of assuming something like that. Right. So moving to the back to the slides. That was the part about the nowcasting, and I will see you for the live lecture on Tuesday. That will be. So I hope you enjoyed it. See you on Tuesday. Bye.